We'll finish up our study into graphs and directed graphs by examining the practical problem of finding the shortest path between two vertices in a graph or digraph that either does or does not have edge or arc weights. Okay, the most popular algorithm by far for solving this problem is called Dijkstra's algorithm, and we're going to learn this algorithm in detail. As I mentioned, we're going to apply Dijkstra's algorithm to an edge-weighted graph. We're going to think of the weights of the edges as conveying a sense of distance between vertices along that edge, okay? And paths we'll think of as having lengths, right? The sum of the edge weights along a path will be the length of the path. The way Dijkstra's algorithm works is by beginning with S, focusing in on S first, and then steadily discovering vertices that are further and further away from S. Okay, so it pretty much radiates out from S. And if the goal is just to get to the vertex T, then the way this is going to work is that by the time we discover vertex T and process it, we'll talk about what that means. By the time we do that, we can be assured that we will have discovered the shortest path from S to T. Of course, we're going to go forward and look at an example, and hopefully, it'll hit you at that point. It's my hope, it's my intention, certainly, that that this next complete example will make Dijkstra's algorithm very clear to you. Okay, here goes. A tiny point. I'm not going to worry about a target vertex, so I'm going to be just interested in starting with a starting vertex S and then just proceeding to find the shortest paths to all the other vertices that can be reached from S. And so when this algorithm is done, when the heap is empty, the algorithm will be done, and at that point all of the information will have been extracted so as to know how to get from S to any of the other vertices that we discover, and we can figure out exactly what the shortest path is. This is the graph that I want to use in this example. In the upper left corner is a vertex that I've labeled little s. I conveniently labeled it little s, so we identify it as the starting vertex. All of the other vertices I've labeled just with capital letters in order. What do we got? A, B, C, D, E, F, G, H, I, right? And we see that this is connected, okay? Therefore, Dijkstra's algorithm should eventually discover all of these vertices, and when it's done, it should know that it should have pulled out the information to easily convey to us shortest paths from S to any of these vertices. As I said, we'll push the vertex S onto the heap. Let's put S onto the heap. So here on the right side is a conceptual view of my heap. Again, it's a reverse heap. It's actually a reverse heap. So anyway, at the moment, S is the only thing in this heap, and its priority is 0, right? What is 0? 0 is S dot D. S dot D is 0. That's always going to be true. S dot D is always 0. Don't forget that these other vertices, like A dot D is currently infinity. B dot D is infinity. C dot D is infinity. Okay? When we put nodes into the heap, we'll label them as a pair, the vertex, comma, that vertex dot D. Right, so the currently known distance from S to the vertex. Yeah, so we start by processing S. While we're processing S, we of course discover three other vertices, A, H, and G. Okay, I'm not particularly interested in the order in which these are discovered, but as we put them into the heap, we could end up with the heap looking like this. Let's say we discover H first. All right, well, when we discover H, something that isn't said in the slide that perhaps should be. Remember that I said H dot D is infinity, right? A dot D is infinity, B dot D is infinity, C dot D is infinity, and so forth. In the beginning, H dot D is infinity, right? Now we're currently using S. Well, what is S dot D? S dot D is 0. All right, well, if we take S dot D and we add the weight of the edge connecting S to H, well, that's 5, right? So S dot D plus the weight of the edge connecting S to H, that's going to be 0 plus 5. 0 plus 5 equals 5, right? And 5 is less than infinity. H dot D is currently infinity. Yeah? 5 is less than H dot D. Since 5 is less than infinity, it's time to change H dot D. H dot D now becomes 5. All right? And H dot pi becomes S. I didn't have any room on this slide to put any more information, but please get this first step in your head, because it's going to be very much the same going forward. H dot D was infinity. H dot D has been changed to 5, and H dot pi is equal to S. Right? Why is H dot pi equal to S? Because S comes just before H on the shortest path from S to H. The shortest path discovered so far. All right. So we've just discovered the vertex H. It's just been discovered, and therefore it gets added to the heap, and it gets added with H dot D as the priority number. Okay, H dot D is equal to 5. We just set that equal to 5. Okay? Similarly, if we discover G next, in discovering G, G dot D was infinity, but now G dot D is going to become 3, and G dot pi is going to be S. And anyway, G gets added to the heap with priority 3, because that's equal to G dot D. Dot D is equal to 3. Yeah, and it's the same story with A. A dot D was infinity. A dot D becomes 6, and so it gets added to the heap with a priority 6. And of course, A dot pi is also S. We're all done processing the vertex S, so its state becomes processed, and I'm representing it black as a black vertex in the graph. And because S has been processed, it is removed from the heap, right? It was at the top of the heap, but now I've removed it. And if you go through the usual heap stuff, you discover that will cause G will get moved to the top of the heap, and H and A will be underneath it. Okay? All right. So now it's time to process the vertex G, because it's at the top of the heap. All right. In doing so, we easily see that there are exactly 2 undiscovered vertices that now become discovered, right? F and I are both neighbors of G. They were previously undiscovered. While we're visiting G, we discover them. We discover F and we discover G. I'm sorry, we discover F and we discover I. We discover F and we discover I. Okay, let's say we process, so let's say we look at F first. Let's look at F. What is the value of G dot D? G dot D is equal to 3. Yeah. If we add to that the weight of the edge connecting G and F, well, that's 6. Okay, so we get 3 plus 6, that's equal to 9. Okay, how does 9 compare to F dot D? Well, it's almost a trick question, right? Because F dot D has just been discovered. So little d is currently infinity. Okay? 9 is certainly less than infinity. Okay, therefore it's time to change F dot little d and make F dot little d equal to 9. F dot little d is now 9. 9 is now the shortest known distance from S to F. Okay? And because we just discovered S, we need to add it to the heap. Okay, so that's easy enough. We see that reflected in the picture. F gets added, and it gets added with a priority number 9 because 9 is equal to F dot little d. Okay? And in a very similar way, vertex I gets added with a priority 12 because we'll have changed capital I dot little d to 12. Okay, 12 being the shortest known distance from S to capital I. All right, so we added 2 new nodes to the heap. What else happens? Well, now this is important, right? We're currently visiting G, and G has 2 additional neighbors, S and H. Okay, well, what about S? Well, S was already processed. We can ignore S. All right? Ignore S. It's been processed. But H, we cannot ignore H. H has been discovered, but H has not yet been processed. So we have to pay attention to H. In the current context, capital G plays the role of little v, the little v vertex that we discussed earlier, and capital H plays the role of the little u vertex that is a neighbor of little v, right? Okay, so here's what we have to do. We have to consider this inequality. Capital G dot little d plus the weight of the edge connecting G to H. Well, let's pause. What is that equal to? Well, that's clearly equal to 3 plus 1, right? G sub little d plus the weight of the edge connecting G to H, that's equal to 3 plus 1. All right, well, that's 4. 3 plus 1 is 4. How does that compare to the current value of H dot little d? What is the current value of H dot little d? Well, it's 5, isn't it? Okay, go back to the previous slide and you'll see that we added the vertex H with priority 5 because H dot little d was 5 because that edge from S to H is 5. All right, well now, of course, something interesting has just happened. 4 is less than 5. 4 is less than 5. We have just found a shorter way to get from S to H. Okay? This might feel a little weird because it takes 2 steps to go from S to G to H, but the total length of that path from S to G to H is 4. That's shorter than taking that edge directly from S to H because that S to H is 5. Okay? So it took us a little more effort to discover this shorter path, but it is a shorter path. Since this is a shorter path, we have to change H dot little d. H dot little d used to be 5, but now we have to set it equal to 4. And at the same time, we have to change H dot little pi equal to G to reflect the fact that the shortest known path from S to H goes through G immediately before arriving at h. Okay? So h dot little d is now 4, and h dot little pi is equal to g. Okay? Since we changed h dot little, we're going to have to change the node priority. We used to have h comma 5 as a node in the heap. We had to change that to h comma 4. But if you notice, that doesn't really affect things here, right? If we change that priority from 5 to 4, it doesn't rock the boat. It doesn't upset the heap. So no need to fix up the heap. Okay? So that's the situation right after crossing capital G, the vertex G, after which we need to remove the top of the heap from the heap, right? We have to remove G from the heap. So after processing vertex G, we'll remove G from the top of the heap, and if we check it out, we wind up with H moves up to the top of the heap. So therefore, it's time to process H next. Okay, let's see quickly what happens when H gets processed. All right? So currently, the value of H dot little d is 4, right? That's the priority of H. It's H dot little d is 4. Okay? Because of that new shortest path we discovered a moment ago. H dot little d is 4. All right, while we're processing H, what new vertices do we discover? Well, the answer is only one, B, right? B is the only neighbor of H that is previously undiscovered. So now he becomes discovered, and let's see. The weight of the edge from H to B is 4. The value of H dot little d is also 4. 4 plus 4 is 8. 4 plus 4 is 8. So therefore, we're going to change capital B dot little d to equal 8, right? That reflects the fact that the shortest path that's been discovered so far from S to B is equal to 8. Okay? And of course, we have to put B into the heap. We add B to the heap with priority 8. Okay. Now, what other neighbors does H have? Well, let's see. S and G. S and G, they've already been processed, so we can ignore them. The only other it has is capital A. Capital A has been discovered previously, but it has not yet been processed. So we do have to check up on capital A. Let's try this. What is H dot little d plus the weight of the edge connecting H to A? Well, that would be 4 plus 3, right? 4 plus 3 is equal to 7. Okay, how does 7 compare to the current value of A dot little d? Well, A dot little d is 6. Okay, is 7 less than 6? Well, certainly not. 7 is not less than 6. Okay, therefore, we did not discover a new, shorter way to get from S to A. And then we leave it alone. We leave it alone. Okay? And that's it. We're done processing H. So we pop H, we remove H from the top of the heap. And then we find out that A winds up at the top of the heap. So we process A. And in doing so, there are no new undiscovered neighbors of A, right? All of the neighbors of A have already been discovered. 2 of them have been processed, so they can be ignored. And only B has to be considered, right? B has not yet been processed. It is a neighbor of A, so we have to consider it. Let's do that real fast. What is capital A dot little d? Capital A dot little d is 6. What's the weightage connecting A to B? Well, that's also 6. All right? 6 plus 6 is equal to 12. Okay? How does 12 compare to the current value of b dot little d? All right? The current value of b dot little d is 8. All right? Well, certainly 12 is not less than 8. 12 is not less than 8, so we can ignore capital B. We don't have to update capital B, and we're all done visiting A. All right? So we remove A from the top of the heap. And then it turns out to be B's turn. B winds up at the top of the heap. And while visiting B, we wind up discovering 2 new vertices. C and D are both vertices that were previously undiscovered. They are now discovered. They get added to the heap. If you check the details, you should be able to figure out that we have to change. We set C dot little d to 10 and capital D dot little d to 17. Okay? You should know how to do that by now. Now, what about the neighbor capital I? Capital I is certainly a neighbor of B, and it has not been processed yet. So we have to consider capital B dot little d plus the weight of the edge connecting B to I. All right, well, that would be 8 plus 3. Okay, 8 plus 3. And that's equal to 11. All right, but if you go back, you'll see that we previously set capital I dot little d to 12. So the question becomes, is 11 less than 12? Is 11 less than 12? Certainly 11 is less than 12, so we have to change capital I dot little d to 11, and we have to set capital I dot little pi to B, right? We're doing those two things because we just discovered a new way, a new shorter path to get from S to I, right? We now know basically there's a way to get from S to I along a path of length 11, right? And how, what is that path? That path would go from S to G to H to B to I. From S to G to H to B to I is a path of length 11. That's the shortest way to get from S to I that's been discovered so far. Okay, we're done visiting B, so remove B from the top of the heap. And then it's time to visit F, and I'll let you check the details on this. It's pretty much the same game. Then it's time to visit C. C will be at the top of the heap, so visiting C. If you check the details on this, you'll discover that we do have to change the value of capital D dot little d, right? The new value of capital D dot little d will become 11. You should be able to figure out why it has to become 11. And then, because we have to change the priority of a node in the heap to 11, winds up we have to fix up the heap a little bit. Okay, but I don't want to get really concerned about heap issues. But it's straightforward to fix the heap up. So then it becomes D's turn. We're almost done. And then it's I's turn, and finally E's turn. Okay? We visit E. There are no other vertices. All the other vertices have been processed already. So that's it. After we're done processing E, we'll have processed all the vertices. And the truth is, we'll know all of the distances from S to all of these vertices. Besides knowing all of the distances, why? Because V, for each of these vertices, little v stands for any of the vertices in the graph. Little v dot d will be the correct distance from S to V. That'll be true for every vertex. In addition, little v dot pi will be the vertex that comes right before little v along the shortest path from S to V. Okay? I didn't have the room to illustrate this, but you should go back and check out the details on that. Let's consider the moment when capital D dot little d was changed from 17 to 11. Okay? If you go back a couple slides and look at that, you'll see that at that moment, capital D dot little pi was set equal to B. No, it was changed from B to C. Okay? And that's because the new shortest path that we discovered went through C just prior to arriving at D. If you check all the details at that point, you'll see that capital D dot pi is equal to C, capital C dot pi is equal to B, B dot pi is equal to H dot pi is equal to G, and G dot pi is equal to S. So that right there gives us a shortest path that takes us from S from D back to S. And then if we simply reverse that path, we then have a shortest path from S to D. Okay? Go from S to G to H to B to C to D. Okay? And you can basically play that game with any vertex as a destination vertex. All right?